to Blackboard. Okay, so I want to keep everything easy for him. He's got enough on his plate. Plenty of time. All right, let's begin with lecture 15. And today we're going to finish up all that stuff on structures, and direct form 1 and 2, and the flow graphs, and kind of move on to something a little more practical, or at least more useful in my mind, which is the design of digital filters using analog filter techniques. And so we'll learn a little bit about the bilinear transform, why that's actually useful for what we're trying to do here, and kind of look at it underneath the hood and kind of see what it does and why it's useful. So with that, let's finish up what we were talking about last time. And to get started, we're going to look at something called parallel form, which we did at the very beginning of class, which I think way back at the very beginning in chapter 2, we could have a system function, and you could, if you put it in if you partial fractioned expansioned it into 2 parts, then you could make those parts be parallel in a block diagram. And we can do the same thing here when we're doing not block diagrams, but signal flow graphs. And we'll do a quick review since this is a little bit intricate here with the all the nomenclature. And this is what, E0K, E1K, and so we end up with this expression here. Remember from last time, one of the things that we like to do is break things into second order sections. Now we're not going to prove it rigorously or maybe show it by using actual hardware, but it turns out that there are many computational advantages when you divide things up into a bunch of second order sections. Typically you can control the gain of the signals, which means you control the dynamic range through the processing. And also the computational, or I guess the it seems like on the average your tolerance compared to the number of bits you have in your arithmetic seems to work a little bit better with these second order sections. So we're going to kind of stick with that for our discussion. So what all this is saying is that instead of having factoring the numerator and denominator into a bunch of polynomials, we can factor them into a bunch of rational factors, so a bunch of sums. And so now we have a parallel form. Now this term here only exists if there are the same number of zeros as there are poles or more. And so we're going to look at that. So you can think of that as the degree of the numerator over the degree of the denominator. And we'll do kind of an example to sort of show what that is. So let's sort of unpack all that with a discrete real example. So suppose we want to implement this system function. So how many ways can we do that? Well, the first thing we're going to do is look at it. The degree of the numerator is z to the minus 2. The degree of the denominator is also z to the minus 2. So that means that should be a warning right off the bat. We need to do long division. So if we do that, we'll just kind of start that process. So all this divided by all that. So z to the minus 2, 2z to the minus 1 plus 1. And all that is divided by, what, 0.125 z to the minus 2 minus 0.75 z minus 1 plus 1. So if we do this, what is that? 8 times 1/8 z to the minus 2, 8 times 3/4. So that's 8 times 3 is 24, over 4 is 6, so that's minus 6 z inverse. 8 times 1 is 8 plus 8. So 1 minus 8 minus 7, 2 minus negative 6 is 8. So we end up with that as leftover. So with that, we can start our first manipulation of this system function and rewrite it now as h of z equals 8 plus 8z minus 1 minus 7 all over 1/8 to z to the minus 2, 3/4 z to the minus 1 plus 1. So we're slowly breaking this down. Now, of course, right here we could just stop and say, well, this is a second order section because it has the highest degree is 2, and we could make an implementation flow graph for just that. So using this, this is in parallel, so we've got 8 by itself, and then we have our second order section, and then we have to sum them back together. I shouldn't put an arrow, that's a sync. So remember our second order sections, our A's are this way. We have what?
All circles are summers, right?
All circles are summers, that's right. If there's everything that goes into it is a sum. Now maybe I should put arrows here then, so you can tell that stuff is not going into this, stuff is going out of it. So what is this? We've got our A coefficients. A1 is 0.125, but if you remember, this is 1. I guess I should have wrote this as 1 plus 0.125 z to the minus 2 minus 0.75 z to the minus 1 to agree with what we had yesterday. But remember, we derived all that form with these coefficients negative, and so since that's positive, that one is well behaved, it's negative. Here's our z inverse. And we've got what? B0 is minus 7. and B1, which is 8, is 8. So we've got here our second order section, abbreviated SOS, second order section. And there's our, just a gain of 8. So pretty straightforward. One way to implement it. But we're talking about how can you really parallelize this completely. So take it all the way to the final step. How would you do that? Well, that goes back to use partial fraction expansion. On h of z, which was what? 8 plus 1 plus 0.125 to the minus 2 minus 0.75 z inverse there. So if we apply partial fraction expansion to that, we're not going to go through all the details because we've already done that before. We can just bring down the 8. We don't need to worry about that. And then we can just apply our partial fraction expansion to this term. And if we do that, I'll just take it right out of the oven so we don't have to go through all that again. And that's 1 minus 0.25 z inverse. So basically we've cracked this thing all the way down to a sum of 3 terms. So the sole purpose of that is now we have something that's embarrassingly parallel, really. Right? So x of n comes in. There's their factor of 8. Then we have one of these terms here, and we have what? If we go with this one, b0 is 18, so that goes there. Z inverse, and that's plus 0.5, right? For A1. And that's, now we have 8 done, and we have this term, which is our second term. All this has to be summed, so. And we've got our final. Minus 25 over this. So if B0 is minus 25, we have that. And A is what? Plus 0.25 with a Z inverse. And we're done. Y of n. So we've broken it up into 3 first order sections. So hopefully this sort of demonstrates, all right, you can get different structures out of here, which can sometimes appeal to your needs depending on what sort of processing elements you have. And our final topic is transposed forms. Or sometimes called flow graph reversal. And the way that this works is you can take a flow graph and rewrite it in a slightly different form. And to do that, you have to follow kind of 3 steps. The first step is you're going to reverse the branch direction. So everything that was going left now is going right. So reverse branch directions. And my little sketches here, that's basically just the arrow. Instead of pointing to the right, now it's going to point to the left. Then you have to swap the input and output. The input and output nodes, which we sometimes should call source and sink nodes. And then the final step is to rewrite the block diagram so everything goes left to right. Because typically that's industry standard, going left to right. So if you have it all going backwards, it can be confusing. So we'll say redraw diagram to flow left to right. To kind of give you a feel for for this, we'll do one quick example and then show a result. So let's do that. So for our example, let's use a pretty simple recursive filter. So y of n is a times y of n minus 1 plus the input. Pretty straightforward recursive filter. So if we take the z transform, move that over, take the z transform, that's 1 minus what? A z inverse equals x of z. Right, and so now we can get the transfer function, or I should say the system function, is 1 over 1 minus a z inverse. So now we've got what we want to do our standard second order section, but now it's really a first order section, and its direct form looks like this: z inverse a, that's a 1 because b0 is 1, and we're done. So now we'll take this and apply our 3 steps and see what it looks like. Kind of give you a feel for what happens here. So the first step is to reverse all the branch directions and swap the source with the sink. So I can do that. Y of n, or x of n becomes y of n, and y of n becomes x of n. So first part done. So now all the branch directions need reversed. So where things were going toward this side, now they're going this direction. And where this one was going down, now it must go up. So we end up with this. And what happens here? And now for the part that's a little more intricate, we just have to look at this, kind of flip it over in our mind and work backwards. Because we want to start with everything on the left and redraw it so we go from left to right. Because right now, what do we have? A flow diagram that goes backwards. Inputs are on the right, things flow through and come out on the left. So typically, take that, flip it over, move it over here. And that's the 1. Then we have the z, which is going up. All right, then we have another branch and then another branch. And that takes us to y of n. This was z inverse. I'm just going to tie this one. That had a coming into it from the next node over, so I'm just going to say that's a coming into it from the next node over. Let's see if I agree with my answer here. Now let's compare these. These are very simple ones, and it's probably nearly intuitively obvious that they're the same graph. Let's see if we can even put them on the same page. Let's see there. So now we've got our original and our transposed form. What's the difference? Not much, because there's not much going on here, right? In the original, we flow through the graph, we get delayed, we get multiplied by a, summed back in, and we flow through. Pretty straightforward, and that's good because that's what that looks like the equation. What happens here? We're flowing through the graph, and we keep going, we're fed back, we're multiplied by a first, and then delayed, and then summed in. So really, all we did was multiply by a first and then delay in the transposed, where in the normal we delayed first and then multiplied by a. No big deal. So to some extent, that seems like it might be fairly obvious. But it turns out for things that are more complicated, it isn't. So what we'll do is we'll just show an example of one of those that's somewhat useful. Is the second order section, direct form 2. And we introduced this last time, but I want to put them all on the same page so you can kind of see how it all works, or see how it all looks. So Y of n, this was our delay tap network here, Z minus 1. Then we fed all these back. Right, that was A1, that was A2. And then the good news on this side was what? This was B0. We fed B1 and finally B2. That was our standard second order section. Now, what does the transposed form look like? Instead of just going through all 3 steps and trying to work that, we're just going to jump to the end, just so you can kind of see what it looks like, and we'll talk a little bit about it. Now we've got what? It's B0 in the delay network, and all the delays are connected. All the B1s are there. So now, what's happening? You can now see we're basically doing the B coefficients first in the transposed form. In the previous one, we were doing the A coefficients first. So we've got what? That's A1, and that's A2. So there's our transposed form. So if you recall back at the very beginning last time, we talked about, okay, what's one way we can manipulate these forms? And we had direct form 1. And direct form 1 actually did the B coefficients first and then finally did the A coefficients. But it required, if you recall, 2 sets of delay networks. And so it was, twice as inefficient, or it required twice as many delay elements as the direct form 2. Now you can see maybe the utility of this is that now you can implement the B coefficients first if you'd like and still use this more efficient form.
Do any of those coefficients need to be negative, or are they all just positive?
They're all positive because there's no step where you have to change the sign of the coefficient and just going from normal to transposed. And that finishes up all the material we're going to cover for the structures for discrete time systems.
I have a question. Why do we need a transposed form? Why bother?
It just allows you some flexibility. Like for the second order sections, if you use this, which a lot of people, you can even find chips that do second order sections in analog form. Says number of poles at a time. The way this is implemented is you kind of work on the A coefficients first in the network, whereas this one kind of does the B coefficients first. They're the first things you start multiplying through. If that's an advantage to you for some reason, maybe the number of bits you have in your system, it's usually the implementation details and the constraints you have. They're going to maybe give you a slight advantage. I think most of the time there isn't going to be an advantage one way or another. Most of the time there won't be. It's a good question. All right, so now let's sort of change gears and move into chapter 7 and start talking about filtering. So in chapter 7 we're going to cover a little bit of IIR filter design and FIR filter design. And we'll start with first of all, we have to figure out, well, how do you, if you're going to design a filter, what do you need? Well, you need specifications, the requirements of the filter. Well, what do those look like? Well, at the beginning of the course, we were just talking about concepts. We use this ideal filter concept all the time. Well, nothing looks like that. In fact, I think we derived, if you just integrate this up and try to get a time response for a filter like this, it's not even causal unless you add the right phase to it and things. So there's some non-real world effects there. But in the real world, you can have a filter that may have some non-ideal effects, like ripple in the pass band. The transition band is long. This would be, what, 2 pi. So I'm kind of drawing it in the discrete frequency. So you have all these 9 non-idealities that you have to deal with. So are those a problem? Well, and the answer, of course, is it depends on your application. Some applications are very tolerant, some are not. But in order to control it, you have to be able to specify it. Because you might be able to tolerate a little, but maybe not a lot. So how do we get there from here? Well, let's sort of do what I'm going to do is go back to this and just sort of excise this part and blow it up. And we're going to look at things kind of like that. And let's say we have a response that looks like that, where maybe the midpoint is 1, and we'll call this 1 plus del p sub 1, 1 minus del p sub 2, and then dot dot dot. What do we have here? We have ripples over here. We'll just call that del s. We have some activity over here where there's, looks like some stuff is happening. The transition band, WP, WS. S is for stop. So in the stop band, we want the maximum attenuation, and we don't really care typically what happens in terms of the ripple, but sometimes we do. So transition band, basically this area in here. So we'll say that's what, WP and magnitude, because it's on both sides, WS. So there's our transition band in this area here. So we're going to go through and talk about what these are. WS stop band. That's where we'll typically specify, oh, I need minus 40 dB or minus 20 dB, minus 30 dB, some sort of attenuation. WP pass band. You may specify the attenuation here at, it's okay if that's minus 3 dB or minus 1. So here it's minus 1, minus 3. Maybe it needs to be 0. And then down here it'd be significantly less. Your del P1 and del P2 in this diagram basically are specifying the ripple. So how much ripple? So this is pass band ripple tolerance. And to design some of these filters, we're going to use MATLAB toolboxes, and they require that as an input. If you want less ripple, you're going to have a higher order to some extent. I think that's how it'll typically work. Of course, if we use the Butterworth, that's maximally flat, which we're going to talk about hopefully today. And what was our del S is our final one. And that is basically the stop band tolerance. So how much ripple can you tolerate in that band? So let's move over to talk about our filter design methodology. We're going to talk a little bit about or show how to do the Butterworth filter today methodology.
One question. Does the stop band tolerance and the stop band omega, does that have any relation?
You're saying the stop band tolerance?
Tolerance and that, does it have any relation? Or?
I think those are. I think those are typically independent.
Okay.
And they. Yeah, I'm not sure. Maybe. Now that's all related to the filter order, which we haven't talked about. But I think these are totally independent parameters. I think if I could spell methodology, that would help. Methodology. With the space in there. So anyway, that's what we'll talk about. So how do we do that? Well, we're going to talk about two different ways. One is kind of using II filters and continuous time filters, and another is the window method. And the window method is sort of a native discrete time method in my mind. But we're going to talk about more of the analog first. And so how does this work? First, in some sense, you're going to design a continuous time filter. And then once you've designed that filter, you're going to convert to discrete time. Using a bilinear transform. Bilinear transform. So that's one way to do it, which is what we're going to talk about maybe today and tomorrow. The second method, like I said, is just design the filter in discrete time. And we're going to talk about that. There's MATLAB toolboxes for all this, but we're going to kind of step through it, design our own in Window, and kind of one step at a time in MATLAB. And you can see, yeah, you can do it yourself. Even if you didn't have a MATLAB toolbox, you could code one up yourself in C and not ever have to worry about it, because we're going to show that what you can do here in classes gives you the exact same answer. So that's the window design method. So those are our two things: continuous time, discrete time. So that brings us to, okay, if we want to use this tool to do the transform, it's called the bilinear transform. What does it do? And a good portion of today's lecture is trying to get comfortable with the bilinear transform and understand it. So what does bilinear transform do? Well, it basically is a mapping between S-plane and the Z-plane and the Z-plane. So it's going to map J omega axis actually that's in the S-plane to the unit circle in the Z-plane. And I guess maybe I should put one revolution in there as a note. So what does that mean? Well, if you think back, way back to when you talked about Laplace transforms, continuous time filters, and control theory and all that stuff, way back in your mind, you might remember poles in the left half plane, that's good. Poles in the right half plane, that's bad, not good. So what is this telling us? This maps J omega axis in the S-plane to unit circle in the Z-plane. Well, it turns out that it also maps everything in the left half plane inside the unit circle, which is good because remember, if you had poles inside the unit circle, that meant several things, right? You could have a stable system. You'd have a system that would have a Fourier transform. So it's kind of nice that stable systems in the S-plane will map into stable systems in the Z-plane. But there's a price to be paid and a few warnings. And we'll kind of go through those. Here's kind of the kicker. We just mapped infinite frequency space to minus pi to pi. So at some point this is going to get highly nonlinear, right? If you're going to map everything, all frequencies to minus pi to pi. So we're going to kind of go through that and see it. And we'll sort of make pictures to show all this stuff after we go through the analysis. But before we start all the math, let's kind of back up and say, why would you really want to do this? What is the utility of the tool? What's the payoff for this? So the real kicker is the bilinear transform basically allows us to use continuous time filter design techniques. And that might not seem like such a big payoff if you're unfamiliar with the literature, but if you look at it, I mean, when did the Butterworth filter paper get published? 1930, that's a long time ago. There's nearly, 100 years of stuff past Butterworth, 90 years of stuff past Butterworth, and there was stuff before that paper too. And, I wouldn't necessarily say that's the high point or anything, that's just a point for us to think, wow, people have been studying this all over the world for nearly, probably on the order of 100 years. Now, wouldn't it be nice if we could use all that stuff in discrete time without having to reinvent the wheel? And that's the point of the bilinear transform. We can use all that theory and willy-nilly design our filters using whatever methods that mankind has dreamed up over the last 90 to 100 years. So there's a huge payoff for understanding how to use it. So how do we use it? Turns out it's going to take, I like to divide things into 3 steps. So we're going to use the bilinear transform, but this is a discrete time filter class, or a discrete time class. And so we're going to mostly talk about discrete time filtering. So the filter specifications and requirements that you have in your hands are going to be in discrete time. That's the assumption. You're in discrete time, you want to do this. We're not talking about building an anti-aliasing filter out of capacitors and inductors. We're talking about, all right, I need to perhaps maybe change the rate, and so I need to downsample this, so I need to low-pass filter it. What are my requirements? So the first step is to convert the discrete time specs, which you get from understanding your system or understanding what you're trying to achieve, to continuous time specs. And you need to do that because you can't design the continuous time filter without continuous time specs using the bilinear transform. So that's step 1. So we've got our specs, we now understand our application. We're going to basically apply a simple algebraic formula. We're going to move the specs, which are what? Things like the pass band, stop band, attenuations, tolerances. Basically, it's frequencies into this. Second step, pull out your recipe book and just design the filter in continuous time. So this is where you just pull out some recipes or Wikipedia or whatever you like. We're going to go through the Butterworth process, so you could code that up and take it with you and do it wherever you want. It's now yours. Use it wherever you like. So you've got that in your hands, and then you're just going to convert h of s, which is basically that transfer function. It's basically the output of this, design filter in continuous time. So I'll say make, get, whatever, h of s. So you're going to go through some process to make the h of s. Now you're going to convert h of s to h of z using the bilinear transform. And the bilinear transform is not like the Fourier transform. It's like there's one formula and you'd apply it to something and pop, there it is. This is basically the bilinear transform, and RSys is like basically two sets of transformations. One to convert frequencies in continuous time or discrete time to continuous time so we can design the filter, and then one set of mappings or transformations to convert this to that. And then that's it. We're done. So to start off, let's introduce one of the transforms that we're going to need. And this is the transform that's used when we're going from h of s to h of z. So I'll say this is bilinear transform. We'll call it equation 1. S, which is continuous time, can be mapped to discrete time using this 1 plus z inverse, where it turns out this t sub d can be any convenient value. And there's kind of more to the story. Usually we're going to go through examples where t sub d equals 1. And once we get through with the lecture, I'll kind of explain where t of d came from and why it's kind of obsolete now. But I threw it in there because the book uses it too. And then everything that we've done here will be in line with what the text presents. And they sort of make the same adjustment. They say, yeah, we make t of d equal 1. But it used to have a more interesting meaning. So if we solve this equation for z, we can get 1 plus t sub d over 2s over 1 minus t sub d over 2s. And what we're going to do is try to explore what are the properties of this transformation. What's going on? So what is S? If you remember, S is just a complex number, right? And typically, you could say, well, S is just some real part plus some j times some imaginary part, which we're going to use omega because omega is that axis. So if we go ahead and substitute 3 into 2, I'll make a note, sub 3 into 2, we can kind of see what this does. So now, z is a little bit more complicated now. If we plug those in there, we still end up with 1 plus, but now it's sigma times this td over 2. So I want to write that as 2 sigma plus j, and I'll make that td to like that.
What do you mean by sub 3 to 2?
Sub equation 3 into equation 2. Just sort of as a note, kind of keep things straight sometimes. And we do that with the denominator. We have that minus sign, so we end up with something like this. So it's kind of getting messy. But we want to see, one of the things we're going to see is what happens to the magnitude of z. So we've got our messy expression here. What happens now if we look at the magnitude of z, which we can get that conveniently by multiplying z times z conjugate. The way I'm going to do that quickly is to think of this 1 plus TD over 2 sigma is just some big real part, A, plus J times some other complicated ugly part, B. And so when I multiply them times the conjugate, I'm going to get A times A. So that's going to give me that ugly expression squared, right? And then I'm going to have this times the conjugate of that, and this part times that, which is going to go away, right? We're going to have the, I guess the cross terms go away because we're multiplying z times z conjugate, or z conjugate times z. So what's left on the top is what? Plus j times td over 2 omega multiplied times minus j td 2 over omega off to the side is the way I'm thinking of it. So j times j is minus, minus times minus is plus. So we end up with td over 2 omega quantity squared. So going through that same reasoning here, now everything's exactly the same, right? Except we had, whoops, left off the sigma. Except now this was minus instead of plus. But making this minus j just meant that the z conjugate part was plus j. So no change. We end up with that. So now we're going to look at what happens. What's the implication? Depending on where S is. And one of the things we care about, as I mentioned at the beginning, is when we're talking about the S-plane, where's all the action? Well, all the action is all the stable pole area, which is in the left half plane. So what we're going to think about is what happens to left half plane poles. So if we just draw a picture to help us remember that, we have j omega axis, real axis, and all this area over here is the stable area. So this is stable area for systems because the poles are in the left half plane. So how can I parameterize that or characterize that? Well, I'll say if this real part is less than 0, which is great because that means I'm in the left half plane, and we'll say that S is some complex number, again, plus j omega, what's going to happen to this function up here at top? Well, let's go ahead and think about if sigma is always negative, what happens to these terms? So we'll have to go a little bit, maybe I'll push it up so you can kind of see these things at the same time. What we want to do is evaluate this ugly expression under the condition sigma is less than 0. We're in the left half plane, and S is this general complex number. Well, if we do that, one way to think about this is what happens to this term if sigma is less than 0? Well, one easy way to say, well, it's just going to be 1 minus TD over 2 times the magnitude of sigma, right? Because sigma, so I'm going to put magnitude, is some number. Since this is always negative, this is our definition, it's always less than 0, then I can always say, well, I'm going to make it the magnitude and put a minus sign there. And that's for the purposes of analysis, which you'll see in just a second. If I do the same thing down here, I've got 1, that's always negative, so it's going to be plus TD over 2, magnitude of sigma, quantity squared. And then we've got this nearly a nuisance term at this point. So what does this tell us in general? Well, these terms are unexciting, right? They're the same, so they're not going to help us make any decisions. But these terms are interesting because this top term is always going to be less than this because this is a magnitude. These other terms are the same. So what this is telling us is the numerator is always going to be less than the denominator. Because for any number you have, it's 1 minus that. This is 1 plus that. These are magnitudes. Well, what is that basically saying? that's saying that this, I guess I should have put brackets like that, is going to be less than 1, right? And so that's inside the unit circle. If we go back to the z-plane, we've got that. So the nice thing is we've mapped the stable area for continuous time. For continuous, if we had an h of s, and you looked at the poles and you said, all the poles are in the left half plane, that system is stable. If we look at this system, we mapped all those poles inside the unit circle. So we know that that system is also going to be stable. So now let's look at one other piece of the puzzle. And I kind of mentioned it at the very beginning. Let's see, hopefully everybody's seen enough of that. Suppose we look at another condition. What if S equals J omega? So sigma equals 0. So where is that? Well, that is just this line in the S-plane. Where is that going? Well, if we look back at our expression for z squared, everything with sigma goes away. So we end up with 1 squared plus all this. So let's write that down. If that's the case, z squared is just going to be 1 plus td over 2 sigma over 1 plus. Well, that's just a very complicated and obscure way of writing 1, right? So that's basically saying this line maps to the unit circle. So this, when mapping over to the z-plane, is unit circle. This is the S-plane. So now hopefully you get a little bit of a feel for what this kind of warping is doing to maybe the poles, or how things are happening to h of s. It's going to be an ugly algebraic thing, because you notice those this substitution. Imagine if you had an ugly expression for s. H of s has, h to the s to the 6th plus, h to the s to the 5th times, this could get kind of ugly when you substitute it in. But really, it's doing all this warping and changing. But at the very beginning, I said it's kind of a 3-step process. The first step is changing the frequencies in discrete time to what are the frequencies in continuous time, because you need those to then design the filter. And I haven't talked about that relationship yet. So that's the next order of business. What is that relationship?
I have a question.
Yes.
Do we choose the value for TD?
Just choose one for now. And we'll talk a little bit about why it doesn't matter at this point. Right after this discussion, we'll see why it doesn't actually matter. You can make an inconvenient value. I think the book uses 1. I don't see why they use 2. So then all those 2's go away. But you can use whatever you like. And we'll get to the reason very shortly. So our next question is, what is the relationship between omega, that's in discrete time, and capital Omega, and saying in bilinear transform? Of course, I had to put in bilinear transform because someone would immediately raise their hand and say, little omega equals capital Omega times t, right? That's right. You've seen that 100 times at this point. So that's why I had to say in bilinear transform. So let's investigate that. Well, let's start with our bilinear transform. Kind of an ugly expression. 1 plus z inverse. And now we're going to use one of our favorite expressions. Z is e to the j omega. Excuse me, sorry about that. And so, availing ourselves of that substitution, we are now down to this. 1 minus e to the minus j omega, 1 plus e to the minus j omega. Well, you've probably seen the trick that one can play when you have a expression of this type, right? You can do the old factor out the average, at least in my mind, I think of e to the this averaged with e to whatever this is. Well, this is just e to the 0, so that means I'm going to take out e to the minus j omega over 2, right? So 2 over td, e to the minus j omega over 2. So that since that was 1, I've got to end up with plus e to the j omega over 2. And that's still a minus e to the minus j omega over 2. We can do the same thing to the bottom. And so we end up with e to the minus j omega over 2. And this part is what? E to the plus j omega over 2 plus e to the minus j omega over 2. So a lot of omega over 2's running around. Well, the good news is we don't need to worry about that. Those are the same, so they go away. And this is just a fancy way of writing what? 2j sine. So we've got t 2 over td times, what is this? Well, that's just 2 times j times the sine of omega over 2. And that whole thing is divided by what? 2. And this expression is just cosine, right? Omega over 2. And we can write this as, well, the 2's cancel, the j's left over, so we end up with j, our 2 over td is still sticking around. But what's sine over cosine? It's just a fancy way of writing tangent, right? So we've got tangent omega over 2. So now we're getting pretty close. We've got a relationship between s and little omega. And so now we have to remember s is just a complex number. And so what we're going to do to figure out the relationship is we're going to match the imaginary with the imaginary and the real with the real. And so if we do that, the imaginary, this has no real part, it's all imaginary. So we can finally say capital omega, take off that j, take off that j, is what? 2 over td tangent omega over 2. I guess we'll say equation 6, if we can get it on there. It's just going to be the reverse of that. It's like little omega equals 2 inverse tangent capital omega t sub d all divided by 2. And so these are the formulas we're going to use. Mainly this equation 5 is going to take a filter spec, like a passband spec, and we're going to convert a passband spec. Let's say someone says at pi over 4 I need to be minus 1 dB, and at pi over 6 or pi over 2 I need to be at minus 40. Well, you take those individual pi over 2, pi over 4s, plug them in through here, and get an omega out. And those omegas would be what you use in the continuous time to design whatever filter you've got. So let's take a look at those or at least take a look at what's happening. As I warned before, pi minus pi. This is little omega axis. This is big omega axis. So what's happening? Is we're mapping all of omega minus infinity to infinity between pi and minus pi using little omega is 2 arctangent omega TD over 2. That's this curve here. And the bottom line for understanding this is what's the significance of it? Well, for certain applications, and one of them is mentioned by name in the book, like a differentiator filter, this does not work very well, the bilinear transform, because of the of what it does to the high frequencies. There's just too much, I guess, compression. The mapping isn't very good, and even going through this pre-warping doesn't help you. But for normal cases, like what we're going to deal with in this class, low-pass filters, high-pass filters, band-pass filters, it's going to work. So let's summarize what we've got here. How to use it. So first off, can be, we'll say, converted to capital omega using this formula. And this is what we're going to use kind of for step 1. We're going to convert frequencies in this domain to this. Then we're going to design the filter. Then we're going to apply the other part of the bilinear transform, which is where I'm going to use a computer algebra package to help me not mess up all the algebra. Because everywhere I see an S in that transfer function, I got to replace it with this mess. And then the key, one of the takeaways, which is not intuitively obvious, but you might have guessed, is that TD doesn't matter. Since it is used basically in both transformations. And cancels out. So that's not intuitively obvious. I don't think you can see that would necessarily be the case just by inspection, but it turns out to be the case. And so you don't need a TD in there. And so the book replaces it with 1. I'm not sure why I don't replace it with 2 and then just make all these equations a little bit simpler.
What do you mean they canceled out?
Because to design, this is for filter design only, so we're designing a filter. I give you a spec of, you need, let's say, a cutoff frequency of pi over 4. And then you're going to design a filter to do that, and you're going to design it in continuous time. So your first step is to apply this formula. So you take that pi over 4, run it through here, get some omega out. And you had to apply some TD to do that. Then you turn the crank and get h of s. Now in your mind you can think h of s does have some relationship to this TD because h of s depended on this. And we're going to see how that happens with the Butterworth in gory detail. But then you have to go back from s to h of z. Because you need h of z, that's what you're going to implement. How do you do that? You had to replace every s with this 2 over TD, and so this TD turns out to cancel that TD and its effects. Even though it's not obvious. I don't think it's obvious either, but it turns out that's the case. And so you don't need to do that. Now historically, it was there historically because people did some, I would think, really interesting analysis. I've never seen this written out, but they took h of s and wrote it as a differential equation. And so if you think back to maybe circuits or some other class where you ended up with saying, hey, we can solve these circuits using Laplace transforms. Where those come from? Well, you had a differential equation, describe the circuit, you could use it in Laplace transforms, you could solve it. Well, some enterprising people decided, hey, I can go straight from the differential equation that describes h of s to h of z by using trapezoidal integration to do the integrals to solve the equation. Now, I've never done it. I've never even seen it done, but supposedly that's why it was there originally. But that's using kind of a totally different method. We're just using algebra here, and it's almost like it's just sort of a leftover from days gone by. But it's in the book, so I want my results to be consistent. So kind of a weird historical digression there. So now with all those tools under our belt and we feel really confident, or at least we understand kind of how to move forward, let's do one example of the Butterworth filter. So we're going to look at Butterworth filter design. IIR. And we're going to kind of only do half of it, just because I want you to be able to see kind of how it is under the hood, so you can literally write your own program to do this. You don't need anybody's help. I think this is in the appendix in the back of the text as well. And later we're going to kind of go through the whole thing, maybe in with some slides that I have. So actually, that's right. We're going to find h of s given n, which is a filter order. Later we're going to talk about how to get the filter order. It's a pretty minor step. It's easy to do, but it's kind of a distraction at this point. So the Butterworth filter is a maximally flat filter. There's no ripple. And it has a very interesting, or very simple, I should say, form for the magnitude response. 1 over 1 plus omega over omega c, which is your cutoff. All that raised to the 2n. So that's the form of magnitude squared response of the filter. Magnitude squared. And that is cutoff frequency. So it's kind of like the end of the passband for these guys. So given that form, where do we go from there? Well, the way this can be derived is we can take this magnitude squared response and write it as h of s times h of minus s, because of the complex nature of s. We can also use, and we'll have to use this, omega over omega c. Because we have omega over omega c here, we can rewrite this as j omega over j omega c, which we'll call j omega is just s over j omega c. And that's going to help, all these are going to help us get started with basically how to find the poles. And I guess the key is h of s has this form, but once we plug this in here, you'll see that it's a little bit messy, right? We've got h of s, h of minus s, and this is 1 plus s over j omega c, all that raised to the 2n, where n is the filter order. And this is pretty easy. You can always do this in MATLAB in like two steps, right? You can. I did it the other day. S is your frequency, omega c is what you choose. Stick it in here, and you can plot the magnitude response. But it doesn't help you in terms of implementation. So how do we find the poles? Well, take the denominator, set it equal to 0. Pretty straightforward, right? So find the poles, set the denominator equal to 0. So we'll say find poles. So we've got 1 plus S j omega c cut off to the 2n equals 0. So we can move the 1 over and end up with this expression. And this should probably remind you of, didn't we do this before with those roots of unity? And we can do that by saying, well, what's an easy way to write minus 1? E to the minus j pi is a good start, but we've got to take into account it can wrap, right? So plus 2k pi, because complex might want to put the j in there, otherwise it'll blow up, right? So minus j pi, which is minus 1, and we also have this plus 2 pi factor, right? And k can be 0, 1, 2, ... This can wrap forever. We don't care. So now we've got this as an exponential form. We can take the 2nth root of both sides and then multiply by j omega c, right? So if I do that, I get s equals j omega c. But now I have to have the 2nth root of all this. And to do that, I think I'll factor out a j pi first. So this is e to the j pi. I've got what, minus 1. Pull out the j pi, I got plus 2k, right? And then it's all divided by 2n. And we're just about done. The last thing is, what's j? Well, we know j can be e to the j pi over 2. It's one way to write it. But when I do that, that's going to make this even uglier, and I'll probably make a mistake. So I'm going to write it as e to the j pi times 2n all over 2 times 2n. Make my life a little bit easier. And so if I want to have a 2n on the bottom, that's what? E to the j pi 2's cancel, so that's n divided by 2n. So now we have a form by substituting in this j of what the poles look like. So S is now omega c, e to the what? We have j pi n. I'll factor out the j pi, just like I did here, make my life easier. But if I factor out the e to the j pi, that leaves an n over 2n, which is good. I got the 2n there, so that means I'll just bring this n up here. And then I've got to carry the rest of this. Minus 1 plus 2k all over 2n. And now let's take a look at what k can be. K is 0, 1, 2, ... And I'll do the spoiler alert. It only goes up to 2n minus 1. And let's just look at it and see if we can figure out why. So when k is 0, this is e to the j pi n minus 1 over 2n. Okay, fine. And we keep going up, counting integers. Nothing seems funky. We get to 2n minus 1. That's some ugly expression. But now what happens? What's the very next integer after 2n minus 1? It's just going to be 2n. So if we plug 2n in for k, what happens? This whole back half is what? 2 times k is now 2n all over 2n. And oh wait, there's some junk here, times pi. So 2's cancel, n's cancel, you end up with 2 times pi. So after you get past that, you're wrapping again, and we don't care about wrapping. We only want the first, 2n minus 1 values. So that's sort of a kind of a quick and dirty way of saying, okay, we got to stop there. And what we're going to do now is basically, this is, I guess I should put S sub k, because if we plug a k in, we get a value. So now, if we're going to design a filter, we're going to choose all poles in the left half plane to make H of S. That kind of makes sense because that's what we want to do. We want a stable filter. So just to kind of make ideas concrete, let's just throw in a number for n. So let's do an example and say n is equal to 2. We've gone through the analysis. We know we need a second order Butterworth filter. So what does that mean? K is 0, 1, 2, 3, because 2 times 2 minus 1 is 3. 2n minus 1, right? 3 equals 2n minus. So we know we're going to have 4 poles total, and then we're going to select the ones that are in the left half plane. So if k equals 0, let's go back to our handy formula that we'll look at to help us along. If we plug in k equals 0, that's S sub 0, which will be omega c, e to the j pi, and n is 2, so 2 minus 1 is 1. 1 plus 2 times 0 is just going to be 1 all over 4, right? So that's 1/4. So we'll say that's omega c e to the j pi over 4. K equals 1. We get e to the j pi, and n is still 2. So 2 minus 1 plus 2 times k. K is 1, so we got that. Divided by 2 times 2 is 4. So we end up with omega c e to the j pi. Now what's happening? 2 minus 1 is 1. Plus 2 is 3, so we got 3 over 4. And kind of so forth and so on. S2 is omega c e to the j pi. This turns out to be 5 over 4. And our last one is e to the j 7 pi over 4. I think for our very last slide, since we're running out of time, we're going to select our poles. So we've got the 4 poles, but where are they? Where do they lie? So let's just draw it out real quick. Sigma, j omega. This was omega c, and I'm drawing it like this because every single one of these poles sort of has a magnitude omega c and some phase angle, right? It tells you where it is in the complex plane. So e to the j pi over 4, well, that's pi over 2. Pi over 4 is halfway. And so this is the omega c e to the j pi over 4 pole. The next one was 3 pi over 4. 1, 2, 3. Right? So this is omega c e to the j 3 pi over 4. And as you can guess, e to the j 5 pi over 4, and finally omega c e to the j 7 pi over 4. So we got our 4 poles. Well, those are the ones in the left half plane, so we're going to grab those and use those to build H of S. And it's just like what you'd think. If you had 2 poles and you were compelled to build H of S, you know, how would you do it? I think we won't get all the way through it, but we'll get close. So we have 2 poles that we've selected. And so H of S is what? 1 over S minus omega c. We're going to choose e to the j 3 pi over 4 because it's in the left plane. 3 pi over 4. And we have another pole. e to the j 5 pi over 4 also made the cut. It's in the left half plane. So now we have a good start on h of s, but we can make some simplifications real quick. E to the j 5 pi over 4 is also equal to e to the minus j 3 pi over 4, which is a useful substitution for us because that means we can kind of clean this up and use some Euler relations, right, to quickly simplify it. So if we do that, e to the j 3 pi over 4, e to the minus j 3 pi over 4. So now we are almost home. We just need to simplify this. And so if we multiply this out and simplify it using the Euler relations, which I hope you can see are going to come into play, we'll end up with s squared minus 2 cosine 3 pi over 4 omega c s plus omega c squared. And kind of for our final cleanup is, say we desire that h of 0 equals 1. So this is a low-pass filter, so clearly if you have a DC signal, you'd like it to be, let's say, 1 out, max gain. So if s equals 0, that goes away, so it's 1 over omega c squared. So what can you do? Give it a gain of omega c squared. And if you simplify this, we end up with square root 2 omega c s plus omega c squared. And we'll stop right here because we're out of time. But now you've seen kind of a long, gory way of getting the Butterworth filter. And next time we will convert this to h of z. So it's oh.
What did you get from second last step to the last step? From your figures.
Oh.
There all 0. And it says S.
Yeah, we ran out of time. I didn't